So, you know, that's just kind of a positive way to look at it. Or it's the last lecture of the previous portion of the course. It's the other way of looking at it, of course. But actually, today what we're going to do is we're going to talk about, what are we talking about? We're talking about the Ising model, which is one of my favorite topics. I mean, it's just really cool. I'm not sure it's like so practically useful, but it's just so cool intellectually speaking, and it kind of gives you a lot of insight into things that can happen when you're doing this kind of processing. So it's got some historical flavor. You'll cry, you'll laugh, you know, it's good. Okay, so let's go to the document camera. There we go. So we're doing section 10.3 here, which is the discrete Markov-random field and the Ising model. And by the way, last time we kind of wrapped up with the idea that Markov chains and Markov random fields are equivalent, right? That was our big result in 1D. But in 2D, they're not equivalent. In 2D, you know, they're distinct. And last time I spent a lot of time looking for the Venn diagram, which I can't find now either. Where is that crazy Venn diagram? Let's see. So this is 19. Right, hold on. Yeah. So, and you should go through the notes carefully so you can understand the proof of equivalence. Because you know, they're a little bit technically complex. But hold on. Where is? Oh yes. Here is the Venn diagram. It shows that 1D Markov chains are equivalent, and in 2D Markov chains, which we haven't quite gotten to yet, we're going to find out that the 2D Markov chain is less general than the 2D Markov random field. Okay. But you need a larger neighborhood for the Markov field to make completely included. But anyway, okay, so the Ising model. So the Ising model is very interesting. It came from this physics around, and my memory is pretty terrible. Okay, so I sat down and did a little bit of history, but I didn't want to write anything that was untrue. So if you read this little section here, hopefully it's correct. I went through some of the early references to make sure my statements about them were true. So basically, around right before World War II, I guess in the 1930s or so, and then up to the, obviously World War II was a very disruptive event. Okay, but people somehow continued to plow forward in terms of doing some basic research, and there was a lot of interest in physics about that time. It was an explosive period of knowledge involving, you know, well, yes, I think that was a bad word. Involving, you know, Albert Einstein, and let's face it, okay, I don't want to hurt anybody's feelings, and I don't, you know, like, okay, you know, not all human knowledge progression is correlated with good things, okay? But there was the development of the atomic bomb, okay? So that was driving a lot of really basic physics research at the time. I think maybe not so initially. Initially, it was just people were just learning things serendipitously, and then people realized that there were applications of what they had learned. Well, there's very, you know, nuclear power and so forth, but not so good applications. But in any case, you know, so people were trying to understand the basic properties of physics, okay, of materials. And so in any case, there was this well known I guess in the 1920s, that there's a thing called the Curie temperature. So, and this is named after Madame Curie, you know, Marie Curie, right? Yeah. Who was, you know, did many very important things, but was very, I guess, discovered. Hold on, I should know this. Marie Curie, did she discover helium? Excuse me? Radium and polonium. Oh, tritium and polonium. Radium and polonium, okay. Yes, he was a huge figure intellectually. And what happened was that they knew that if you have a material, okay, phenomenologically, if you take this material above some, so let's say this is a piece of material, okay, and it's like a ferrous material, okay. So if you put it in a magnetic field, you can magnetize a piece of metal, right? Everybody knows that. So it turns out that below some temperature, we'll call it T sub C, the critical temperature, a very small external magnetic field N, okay, will cause the material to spontaneously magnetize to a particular direction. And then when you raise it above that temperature, it will lose that. Okay, so we'll retain that, and then above that temperature, it'll lose that magnetic orientation. So this has actually been used in physical devices. So for instance, they're not so popular now, but they used to have optical CD-ROMs. So what they would really do is they would have like a coil. So this is the disk, right? And they have a coil, and the coil they would control the magnetic orientation by controlling the direction of the current, right? And then they would have a laser. So I don't know how to draw a laser. That's a laser. And the laser would heat the surface, okay? So what they would do is they would heat the surface, apply the magnetic field, and then turn the laser off, and then the surface would cool, and the magnetic field would be permanently stored there. Okay? So you could actually encode information by the magnetic polarization at that point. You could also read it out. Well, you could read it out like a typical magnetic material you would read out like a tape. But anyway, so it's been known for a long time that there was this thing Curie temperature, and it's effectively a nonlinear effect because you get a discontinuous behavior at a particular material temperature, okay? So people were trying to understand this, okay? So what they did is the first thing they did is they said, okay, well, we're going to come up with a model for a material. We'll start off with a one-dimensional model because one dimension is really simple, okay? And we'll say, well, okay, there's going to be an interaction between neighboring particles. So let me see. So the interaction is this. You say, well, the energy of a particular particle here is going to be, so each of these, this is like x1, this is x2, this is x3, this is x4, this is x5. You take, say, x, S and x, say, s minus 1, okay? And so each of these particles can be either plus or minus 1, right? So the particle can either be a positive or a negative polarity. So if you multiply them together, then if they're the same polarity, then this will be plus 1, right? And if they're opposite polarities, then it's minus 1. Now, what will happen is that you have the two particles. Okay, imagine these two pens are two particles. And like if you have two magnets, and if the two magnets are aligned, right, they go snap and they go together. I should have brought two magnets with them, okay? And then if you take the magnets and you put them like this, okay, you have to hold them there. And as soon as you let go, it goes snap, right? You've had this happen, right? So the magnets want to align, right? So the energy of the magnets is higher if they're misaligned, correct? Because it wants to roll downhill to the lower energy state, right? So what happens is the energy is higher if they're misaligned. So if it's minus 1, the energy is higher. So therefore you have to put a minus sign here. And of course there's some constant associated with this, so we'll call that constant J. So actually the energy change when you flip states from a line, so when you go from this state to that state, the energy goes up by 2J. So that's the potential energy associated with a pair of states, and then you sum this over S, and that's going to be the total energy. We'll call that U of X, okay? Right? So that's the total energy of the system. Now, there's another thing that happens, which is just fascinating, okay? I'm sorry, you have to be subjected to my enthusiasm. So, I mean, this is just so cool, okay? If you have any system, okay, any physical system in thermodynamics, and you have, it's got, this is the energy, right, of the system. And the state here is discrete. So this is discrete. It takes on a discrete set of values, okay? And then what you can also do is you can define okay, so this is the energy, right? And then there might be some distribution of the energy. So P of X, that's just equal to the probability that X equals some particular state X, right? Okay. Now with this probability distribution, you can define the energy. The energy here is going to be what? Well, it's going to be the sum over all possible states of the energy of that state times the probability of being in that state. So that's actually not just the energy, it's the expected energy. Right? So it's equal to the expected value of U of X. Right? And then you can also define a thing called the entropy. So the entropy, we'll call it H, is going to be equal to the sum over all states of the negative of the probability of the log of P of X. Okay? Okay, so that's the entropy. Okay, and I think people kind of know what the entropy is from information theory. So entropy is very important in thermodynamics. In fact, there's two laws of thermodynamics, and I think I told you about this. The first law is conservation. There's three laws of thermodynamics, actually. But the first law of thermodynamics is, there's three, but there's two really important ones, okay? The first law is conservation of energy. So the total amount of energy in the world has to remain constant. Now, with Einstein, that got modified slightly because E equals mc squared, okay? But basically, in the classical case, energy is conserved, okay? Then, the second thing is that entropy must always go up. So when people talk about the energy crisis, I think I mentioned this before, it's kind of silly. I mean, you can't possibly run out of energy because the amount of energy you have can't change. But where you kind of have a problem is if you have too much entropy, okay? Because you can't just, and I think I gave this example before, you can't just have a boat. Okay, this is the ship at sea. Okay, so this is the ship. Okay. You can't have a ship at sea that just ejects ice cubes and powers itself by ejecting ice cubes. That would be fine because it wouldn't violate the first law of thermodynamics. The total amount of energy is conserved. You throw out an ice cube and use the energy to run the propeller. Okay? It seems fine, right? But what it does is it violates the second law of thermodynamics, which is that the entropy is actually going down. So the entropy has to go up. And in this system, the entropy is going down. So that can't happen. But so entropy is very important. And then you say, okay, and this is essentially, so if you believe that a system, if you believe the first two laws of thermodynamics, I mean, how do you prove conservation of energy? Well, you can't, right? I mean, it's just an assumption. It's an axiom. It's like saying that there's a number which has the property that when you add something, you get the same value back. and we call that number 0, right? It's an axiom, right? So, conservation of energy says that the energy has to remain constant, okay, in a closed system. And entropy says that the entropy only goes down. So if you have h of time, it's got to be greater than or equal to h. So this is T1, T0. If T1 is greater than or equal to T0. So as time goes on, the entropy has to go up, okay? Now, that means that if the entropy can only go up, well, once you reach a state of equilibrium, the entropy is going up and up and up and up and up, it gets to its maximum value, okay? So, well, what's the maximum value of entropy? Can it just go to infinity? Well, it can't go to infinity, and the reason it can't go to infinity is because there's actually a constraint on the energy. So, intuitively, you have more entropy in a system if the distribution of the states is more uniform, right? So, as the amount of uncertainty of the system increases, if all the probability is just on one state, then there's no entropy, the entropy is 0. Because then the probability is 1, and the log of 1 is 0, and so this is just 1, this is just 0, okay? But as the distribution of probabilities becomes more spread out, then the entropy goes up, okay? Now, and as the number of states that the variable can take on becomes larger. That's why it has to be discrete, okay? If it's continuous, the entropy can go to infinity. But if it's discrete, the entropy can't go to infinity unless the energy does. Because now, if you have a finite number of states, the highest entropy you can have is to be uniformly distributed over all the states. But if you have a countably infinite number of states, you could have infinite entropy if you allow the energy to go to infinity. So, the idea is this, that you can argue that you want to if you maximize over all distributions, you maximize the entropy, right, subject to a constraint that the energy, which is also a function of P, is less than or equal to some value, right? That's going to be, I'll call it P star. This is a beautiful thing, by the way. So there's some distribution, presumably, which maximizes the entropy subject to a constraint on the energy. Yeah?
So the number of states must be countable and discrete.
Yeah, if it's uncountable.
Yeah,
so that actually raises a very fundamental question. I'm not a physicist and I'm not a historian. My understanding is that this is how the physicists first started getting the idea about quantum mechanics. But because if you believe that the world's continuous, then the entropy can go to infinity. Okay? And they were like, so the first thing they did is they said, well, let's make a fudge factor, and we'll just assume that everything is quantized, so the number of states is finite, is finite or countably infinite. Okay? Actually finite. Okay? So, and they found, okay, if you didn't assume that the number of states is finite, then nothing worked. Okay, but if you did assume they were finite, then it worked. And by the way, there's some actual physical phenomena. There's a thing called black body radiation. Okay, so if you have a material at some particular temperature, like say, I don't know, pick some temperature. Oh, this comes up a lot in like color science. So you say, what do they call that? Oh my gosh, see, I'm teaching the wrong course right now. What do you call that standard color?
D65.
D65. I think that's either 65,000 degrees Kelvin or 6,500 degrees.
500.
That's what I thought. Okay, so this is 6,500 degrees Kelvin. Okay? So, why do they say that as a color? Well, it turns out there's a thing called the black body radiator, and you can actually derive equations for this. And if you assume finite numbers of states, then you get that the distribution of emission as a function of actually a frequency, I'll call it mu, we could call it wave number, it will eventually go down. If you don't assume that the states are finite, then this will just blow up. Okay? So there's a lot of things that just don't work unless you quantize the states. So that's where they first got the idea that quantum mechanics was might be a good idea. Okay? So now, the bottom line is that now we want a distribution which, subject to the constraint on the energy, maximizes the entropy. So now, it turns out you can work through that, and if you go to Appendix B, I've actually worked it out. So I actually worked out a simple little calculation PC, where I did the calculation. And what you do, so we're looking at equation, let's see, B1. So you can set up a constrained optimization problem with Lagrange multipliers. So you take H here, you're maximizing H, and then you subtract beta, which is the Lagrange multiplier, times the change in the energy, because you want this to be 0. So you want E to equal E0. That's your constraint. And you have this other constraint that the probabilities have to sum to 1. So now you have two Lagrange multipliers, and you differentiate this with respect to P of x, which is, there's actually, if you have, in other words, you're computing the derivative with respect to the probability of each individual state, and that has to equal 0. So if you just compute the derivative, you get the following equation, you just work through it, and you get the following equation in B3. I mean, it's a miracle. You get this equation here, which is that the probability distribution has to have this form of an exponential, e to the minus beta times mu, okay? And the z here, well, that obviously has to be the sum of this thing. It's the partition function, because otherwise it wouldn't be a probability density. So you have the beta, the one Lagrange multiplier becomes the multiplier in front of the energy. Well, now the question is, this thing here is called the Boltzman distribution, or the Gibbs distribution, same thing. In physics, I think they call it more commonly the Boltzman distribution. So, it's a miracle. You can write down the distribution of the states of any system that's in thermodynamic equilibrium. It always has the same form. It's the Boltzmann distribution, where mu here is the energy, and beta is, well, what's beta? Beta is 1 over the temperature. It's actually, technically speaking, 1 over the temperature times the Boltzmann constant. So that the units work out, because temperature here is in, say, degrees, and then the Boltzmann constant is in units of inverse degrees, okay? So, and this has to be measured in Kelvin, because when T is 0, that's 0 temperature, right? And then you can pick T. T becomes the Lagrange multiplier that you pick that will achieve any particular amount of energy, okay? So as T goes, let's see, down, so as T goes down, the energy will go down. And as T goes up, the energy will go up, okay? Well, that actually makes sense, because we know that if the temperature is high, I mean, if you want to raise the temperature of water, you don't put it in the refrigerator, right? You put it on top of a burner, and you add energy to it, and then its temperature goes up, okay? Because you can, right? And then this is the distribution of the state of the molecules in the pot of boiling water. Okay, assuming it's in thermodynamic equilibrium. It's not in thermodynamic equilibrium because you have bubbles coming up through it, okay? But if you let it sit there in a styrofoam container so that everything equalizes to the same temperature, it would be in thermodynamic equilibrium, and then it would have the Boltzmann distribution. It's a beautiful thing. I'm sorry, I'm oogling over it a bit, but it's just really so cool that it works out that way. And, I should also mention that there's some other interesting things that you can prove, like that you can get some different relationships here. They're kind of interesting. So that you can show that the temperature is the ratio of the change in energy per unit change in entropy, which is interesting. So how many people think, so you think you can have a negative temperature? You can have a negative temperature. Isn't that scary? It's possible to have negative temperature, okay? So it can get worse than 0 degrees, okay?
You can have that in centigrade though.
So what you do is, yeah, well, no, you can have it in Kelvin. And the way it works is this. There's some systems that if you drive, I'll give you an example later on. If you drive their energy up high enough, eventually their entropy will go down instead of up. See, normally as you put more energy into a system, the number of available states increases, right? But if you push enough energy into a system, eventually you can drive every molecule to its highest state, and it's as if I'm like trapped in a room, and the water is filling the room up, and I have my head like poked up into the upper corner, and I have very little ability to move around, right? So I'll draw a picture of my, as one of the things that happens when you're exposed to me is you're exposed to my twisted thinking, okay? Okay. So it's like, imagine that you were in a big room like this, okay? And initially, you'd be sitting at the bottom, okay? You'd be standing here, okay? So the room is shaped like a diamond, okay? So you'd be sitting here, and you'd be trapped right in the bottom corner. You try to climb the walls, and they're slippery, and you fall down to the bottom, okay? And then you have over here, this is like some kind of thing in Star Wars. So the water would start filling the room up, okay? And then what would happen is the water level went up. You notice I say water instead of water? That's because I'm from Philadelphia. Okay? But as the water level went up, okay, you would sort of float, hopefully. So you'd be over here. Okay? And you now have more room to move around. So eventually, you would get up here, okay, and you'd be floating around over here, right? And you'd have the most room. But as you pump more and more water in, eventually you start having less room, right? And then your entropy would be reduced. So over here, as you raise the energy, your entropy goes down instead of up. And you could have negative temperature. It's kind of an interesting phenomenon. It actually can physically occur in real physical systems. It's kind of an interesting idea. But yeah. So the bottom line is this. You know that the probability distribution of this physical system is going to be given by 1 over z times the exponential of minus 1 over k dt times u of x. Because it has to have a Boltzman distribution. And keep things simple. I'm going to just write this as beta. 1 over k dt, I'm going to write it as beta. The inverse temperature. We'll work with inverse temperature rather than temperature. So going back to the original 1D case, so we have the sequence of states, the sequence of magnets, and their energy is related by the sum over f of this difference. So that's actually equation, hold on, that's equation, hold on, 17, oh hold on, this, oh here it is. That's equation 10.4? Yes, that's equation 10.4. So it's just a sum of neighboring pixels, okay? And so you have the sum over the pixels, right? So this is the energy, and then the probability distribution is P of x equals 1 over z times e exponential of minus beta times u of x, right? Now, what can you say? First of all, this is a Gibbs distribution. So it's a Boltzman distribution or a Gibbs distribution, same thing. So since this is a Gibbs distribution, what do you know about this object over here? It's a Markov random field, okay? In 1D. Yeah. Now, if it's a Markov random field in 1D, what do you know in addition?
Markov chain.
It's got to be a Markov chain. So X is a Markov chain. Wow, you guys are good. You must be reading the notes. Very impressed. So this is a Markov chain. Now, we're going to use all our knowledge. It's going to be wonderful then. Okay? So, if I start off in some initial state, x0, okay? And then I ask, well, what's the probability distribution as I get further and further away in time, okay? What do I know about the probability distribution? Well, yeah?
I guess it's just a product of the transition.
Yeah. Now, is this a homogeneous or a non-homogeneous Markov chain?
It's homogeneous.
It's homogeneous because it's not a function that, because these potential functions, I mean, you'd have to show it, but the potential functions are not a function of time, right? Okay, is it irreducible or reducible?
Irreducible.
It's irreducible. Why?
Because all states are connected.
Because all the states are connected with a probability greater than 0, right? Is it periodic or aperiodic?
Aperiodic.
It's aperiodic, right? Because, yeah, I mean, I mean, it's just because you can bound, because from one state to the next, if you can go from any state to any other state in one transition, then you know that it's got to be aperiodic, okay? So, it's not, so it's aperiodic, it's irreducible, and it's homogeneous. So what do you know about it? What's the most important thing we learned in the last chapter? If you have an irreducible, aperiodic, and some of you have computers and you can cheat, and that's okay. You have an irreducible, aperiodic, homogeneous Markov chain. What do you know about it if you run it long enough? What? It's going to reach a stationary ergodic distribution, right? And what's the ergodic distribution? It's the solution to what? How do you find the stationary distribution of a Markov chain? I mean, ergodic Markov chain. What set of equations do you have to solve?
Oh, full balance.
The full balance equations, right? So you basically say pi times p is equal to pi, right? So, okay, so we know there's a steady state distribution. So since we know there's a steady state distribution, what do you know? You know that if you wait long enough, whatever the initial state, does the initial state make any difference?
No, the conversion, sorry.
No, it doesn't make any difference because the convergence is independent of the initial distribution, right? So in 1D, you know that the steady state distribution of the Markov chain is independent of the initial condition, right? So this does not exhibit the memory effect of the Curie temperature. There is no critical temperature here, okay? Because its initial boundary, it eventually forgets it's like an undergraduate, okay? It forgets everything you teach it if you wait long enough in the exam, okay? You started in some state and it goes off forever one, okay? Okay, now, so what happened was that they went through a lot of analysis as this guy, let me see. Some here, okay, somewhere in here, okay. However, in 1D, the Ising mode no longer exhibits the critical temperature behavior. I'm reading this on page 220. That's because it forgets its initial state if you wait long enough. That's because a Markov-Random field and a Markov chain are equivalent in 1D, and if you run the Markov chain long enough, eventually it reaches an ergodic distribution, which is independent from the initial state. You cannot hope to achieve the behavior that they were trying to model with physics. They knew that the phenomena occurred physically. And they're trying to come up with a mathematical model that captures the physical behavior. And they found that this is hopeless. You can't do it here, because no matter how long you wait, you'll never get the behavior that you want, right? So, okay, so now they said, okay, so this guy Pearl came along, and another guy Onsager, and you can read my writing because I forget exactly the details of who did what in exactly which order, but I figured it out and wrote it down. But basically, this guy Pearl came up with an argument for 2D that in fact in 2D this phenomenon did occur. And that's consistent with what we know, because we know that in 2D, Markov random fields and Markov chains are different in 2D. So, if we redo this thing in 2D, so we have now a situation like this. And now we have energy terms between pairs, say with a 4-point neighborhood. Onsager, by the way, got a Nobel Prize, but I don't know if he got it for this. He might have gotten it for something else. He was a very smart cookie. These arrows here represent energy between adjacent terms. Okay? So now what happens is you sum over minus j times xs times xr, and you sum over clicks of 4-point neighborhoods, and that's your energy U. Okay? Now, this is a Markov random field, because these are potential terms between neighboring pixels, and it's a 4-point neighborhood, and it's a Gibbs distribution, so it must be a Markov random field. Now, in particular, it's called an Ising model. Although Ising didn't really do that much. I think Ising just proposed the model at some point, and then everybody started calling it an Ising model. I forget, but Ising I don't think did that much in terms of actually proving any properties of it. In fact, Ising I think proposed the original model wasn't even 2D. I think that was the 1D model. And then, read my notes, I went through it and tried to figure it out. But in any case, okay, now in this case, things are different. Oh, by the way, you can calculate the conditional distribution of a point given its neighbors, and you should go through this calculation, 10.7 and 10.8, and you can plot it. And basically what happens is that pixels want to be equal to their neighbors. So on this figure 10.3, if as the number of neighbors not equal to 1 goes up, then the probability of being 1 goes down, okay? Because it wants to be like its neighbors. And that's a faster relationship if beta is larger, because the energy increases more. So if beta is larger, then the energy of the two things being in opposite directions is greater, okay? Okay, now the interesting thing is that in 2D, if you use a 4-point neighborhood, then if these are pluses and minuses, then what happens is that in this figure 10.4, you can think of the total energy term as being the length of the boundary that separates the pluses and the minuses. That's figure 10.4, right? So essentially, the energy here, U of x, is really the boundary length times the constant, I think, 2j. Oh, so if you define beta correctly, I think you want to define beta as being, if you define beta as 2j over k bt, then if you properly normalize it, then mu here is equal to beta times the boundary length. Okay? So, That's this equation on page 222. So then the question is, as beta goes up, does the boundary length get longer or shorter? So if beta is larger, it means that longer boundaries have higher energy. So would you expect the boundary length, typical boundary length, to go up or down as you raise the beta? So beta is the cost of a boundary, basically, because energy represents cost. Okay, so the higher, so you're making it steeper cost, more energy, in order to have a longer boundary. So would you expect the boundaries to get longer or shorter?
Shorter, right?
That would certainly be logical, except where it's not true. Okay, because in fact the total amount of boundary length gets shorter, but indivisible boundaries get longer. So you get a smaller number of longer boundaries is what happens, okay? But, okay, so the key is this. You can show in 2D that if you take a point in the center of the field, that the probability, this is the part that's really cool, okay? I need like a drum roll or something at this point. And I'm going to tell you the key thing about Markov-Random fields that makes this interesting. That, so Ising models in particular. So if you have a boundary, okay, so you have a Markov-Random field, and around the boundary you put +1. Plus. Okay? You make this stuff all plus. Okay? And now you say, what's the distribution of the things inside? And then you make the size of this thing, n, go to infinity. So you take the random field and you put pluses on the boundary and you make the size of the field go to infinity. Now, if there's any justice in the world, you would certainly imagine, just like in 1D, that if you get further and further and further from this initial starting point, that the undergraduate will forget everything that they learned, right? And you would certainly expect that like these people on the outside are TAs, okay? Okay? And the people on the inside of an undergraduate, as you get the classroom gets bigger and bigger and bigger, the student in the very center of the classroom should be insulated from the information, right? Okay? So, well, guess what? It doesn't happen. If you take a pixel in the center and you say, well, what's the probability that x0 is equal to, I want to do this the right way, is equal to -1, given that the boundary is equal to 1, even as n goes to infinity, this thing can be bounded away from 1/2. You would think that, if you get far enough away, eventually the 50-50 chance, the coin flip, it's either plus or minus, but that's not true. The information in the boundary persists even as it goes infinitely far away. And so this can be strictly less than 1/2. Okay? And so the intuition here is this, that the material, but this is only true when the temperature, beta, is greater than some critical temperature. When it's less than some critical temperature, then this will hold. There will be 1/2. But if greater than this critical temperature, then what will happen is that no matter how far away the boundary gets, its effect will never go away. And the reason is, the intuition is this, that the random field is like, it wants to be, below some temperature, the pixels nearby want to be correlated and they remember what each other's are. So below some temperature, the critical temperature, or above, when beta is above some critical value, that it will be, the random field, samples from the random field will either be mostly 1 or mostly -1. And what will happen is that if you make the boundary all 1, you're providing just a little nudge. There's like some kind of book about this. This guy, Gladwell, this guy about, this is the original nudge, okay? This is the mathematical representation of the original nudge. By providing this little tiny nudge around the outside, you flip it so that it's going to be mostly 1.
Whereas
If you had put the boundary either free or made it plus or minus 1, it would have been agnostic, and then the probability would be 1/2. But even in that case, what will happen is that the correlation between 2 points in the field becomes positive, can be bounded above 0, regardless how far the points are away from each other. That they can be infinitely far, no matter how far away they are, there'll a fixed amount of correlation between the 2 points. Because the random field is mostly all 1s or mostly all 0s, and as they get further and further apart, they still are correlated by that amount, right? It's as if you did a coin flip first to decide if the field was going to be 0 to 1, right? And then no matter how far most the pixels were apart from each other, that initial sort of setting, okay, matters, okay? So now the proof of this is in example 1, and I kind of go through it. I guess there isn't a much time. Maybe you're going to have to go through this yourself. Oh, it's such a cute proof, too. You promised me you're going to read the proof? This is kind of clever. I mean, what happens is that I translated it to make it simple. But basically, I'm able to bound the probability of that pixel. I just adapted a proof from a book by Kinderman and Snell. And but it, it kind of goes through it, and essentially what happens is that you can show that you can bound this thing by an exponential of the beta times the length of the length of a boundary that's circumscribed to a point, and then you just count the number of boundaries. You can't have an infinite amount of boundaries because of this issue of it being 2D. Okay, so interestingly enough, Onsager actually got a closed form expression in the case where the lattice was infinite. This guy is very smart, okay? I mean, the arguments he used, back when they didn't have fast computers and they didn't have TVs, people had more time to think. And, I think that, I don't know, their brains got more exercise or something because they came up with very clever arguments, okay? So he shows you can calculate the conditional expectation of the pixel in the center given that its boundary is 1. So this basically tells you the probability because there are only 2 possible states. So by knowing the expectation, you know what the probability of it being 1, 0, minus 1. And this is a closed form expression. It's amazing, okay? And over here, I think I have a plot of the closed form expression, but I gotta find it. Where's the plot of the closed form expression? Oh shoot, we're running out of time. Oh, here it is. There's the plot. So what happens is that as the temperature below, this is the inverse temperature, beta, and this is figure 10.5b. As the temperature goes up, and 1 here is the critical temperature, okay? And the critical temperature can be calculated. Do we have an expression for the critical temperature? Okay, well, if I think it's around. Oh, it's 0.88. Okay. So at the critical temperature, this curve goes up because what will happen is that as the temperature gets higher and higher, the probability that the pixel is 1 gets larger because the boundary was 1 and it inherits the probability from its boundary. And it's a very abrupt effect. And now this is capturing the physical phenomena that they observed with the Curie temperature. So this is a major discovery. And these are 2D lattices. So they got 2D. In 3D, the same thing kind of happens, but you can't get closed form expressions. In 1D, it doesn't. So there's a fundamental change that happens when you go from a 1D lattice to a 2D lattice. Let's see. And then you can go through all this stuff. I just have more detailed things. But, yeah. Oh, I know. I wanted to point out this last thing about the negative temperature, because that's kind of cool, and I think there's a homework problem on it. So the negative temperature, Oh, we're out of time. Shoot. Well, I'll let you think of the negative temperature thing. Basically, the negative temperature occurs if you have pluses and minuses. So if you drive the energy of the lattice all the way up to its maximum, then you have like a checkerboard. And then you have zero entropy because there's only two states that work. Bye.
Where are you gonna stop?
Well, maybe not zero entropy, but very low entropy.